Did anybody come with any particular questions?
I have like general stuff that I know that I suck at.
All right, let's list it. So everyone can know what you suck at.
Okay.
Huh?
A lot of stuff in Norton, like with the load stuff in particular, because sometimes I can't calculate that, and then just utilize it to superposition.
Wait, whoa. You said Thevenin and Norton, like when I say like solve for Vx before you even do the Thevenin and Norton?
It's like sometimes when I calculate with the load and without the load, like, it's just, I'll do it in my head. I just like seeing it done better, and then I have the process.
All right, so we'll just say Thevenin and Norton examples. Any other particular topics? We'll just list all the ones here that you guys think you need help with. Mesh?
More than two.
It's only 2 or 3, so I'll just say mesh analysis.
Specifically,
The recent quiz.
Oh, that's AC, like steady state. Yes, it will. No, not just because you asked. I already wrote the final.
Really?
I finished it today. All right, so we got.
We used 1 week when we asked about the particular topic.
I mean, honestly, everything that you list is probably on the exam. I tried to cover everything. There's no topic that's missing. So.
How many questions is it?
It's 10, but if I think it's too much, I'm gonna reduce it. So it wouldn't be more than 10, but I made it 10. I think 10, and I gave you an hour and 15 minutes to do 6. I think 2 hours to do 10 is like scalable.
Can I take the exam early because I have 3 exams on that one?
You can't schedule that with me. You have to talk to the registrars about that. I think that you can figure that out. I think it's better to just take them all at the same time.
Yeah, I know.
I would. I liked it better. One semester I had all 3 finals on a Monday, and I was so glad. Just get it over with, like, because finals week is treacherous.
That just sounds like a 13th reason.
Yeah, I mean, yeah, it was controls, feedback controls, CS, and Baker's like 420 in the same day. Yeah, it was rough, but I got through it.
Do like a few examples of like current dependent rotations?
Oh yeah, the dependent sources, yeah. Okay, so Thevenin and Norton, mesh and superposition, AC steady state. This is, just so you know what AC steady state is, it's just the stuff we've been doing with the capacitors, inductors, resistors, having impedance, and finding their phasors. I'll just call it like phasor problems. Dependent sources, anything else that you can think of?
You go over Ohm's law?
I could go over it. It would take me a total of 7 seconds. I'm gonna not go over Ohm's law. I don't even. It's actually like derived from Maxwell's equations, and our 330 professor derived it in 330. Yeah, it was pretty. It's something I'm physically not able to do. I don't know the math that well.
Seems like you can derive it. I just don't know how to.
You can. It can be. It's derived from Maxwell's, like those 4 equations. I don't even know them. I probably should. I'd say by the time I have my PhD, I'll probably know them. I would hope so. Okay.
Considering a PhD is like a master of this stuff.
Yeah, that's a master's. No, I should know them by 5 years from now. Get back to you then.
I'm gonna get an email 5 years to the date.
All right. Well, I mean, we can look through the list of topics in case anything. I know you guys need help with charge sharing because people still. Does anybody? Do you even know what that is?
It's like when you have a Samsung, you can charge your AirPods.
It's this. I do this every time. It's the quiz. Did you see that I posted all 16 quizzes?
Yeah.
Quiz 11 is the one. This one.
Oh, I forgot we even did this.
Yeah, definitely study this. Definitely study this.
Wink.
There's your wink. Definitely study this is enough of a wink. Definitely study this. Let's see what else. Definitely. Thevenin and Norton, obviously. mesh, superposition. I mean, I could literally tell you what the 10 problems like regard, but it's just going to be everything. So you're going to be like, well, what was the point of that?
They're going to regard it week 1 to week 15.
The first problem is just like a general like. Oh, sorry. Hold on. So the first problem is like a general, like a solve for the voltages, just using Ohm's law and nodal analysis. I'm trying to think in my head because I don't want to pull it up, obviously. The second problem is, oh yeah, it's basically going to test your ability to know what inductors and capacitors look like in DC. What's a capacitor in DC? It's open. What's an inductor in DC? Okay, that's the second problem. There's a superposition one. There's a mesh one. So that's 4 problems. There's one similar to, analyzing waveforms like we did on the last homework, like analyzing the lag, lead, determining the amplitude, the frequency from the plot. So if you did that on the homework, it shouldn't be hard. If you want me to go over that, I can. I don't care. I'm referring to this problem in case you don't know. Yeah, this. There's going to be one like this. One of these, some particular order. I think that's 6 so far. There's definitely a Thevenin and Norton, so that's 7. Oh, there's an RC, one of those two, plotting the waveforms, like one of those quizzes. Basically similar to one of these quizzes where I gave you the plot and asked you to plot it.
Basically, all
Pretty much. That's 8, or that might be 9. And then there's like 2 little 5-point problems that are just like easy. They're like not easy, but they're like conceptual. So I think the 8 problems that I just listed make up 90 points, and then there's 2 5-point problems that are like, it's either you know the concept or you don't. And those are just 5 points, so that's...
Like written or something?
No, there's still circuits, but it's not like intensive math. It's just like, do you know it or do you not? If you don't know it, you're going to be in trouble. Just know that I'll cover them during the review. So if you study everything that I tell you to study, you should be fine. But you should study more than just what I tell you to study, because if you want this on the exam.
I mean, why not, right? You either know it or you don't.
50 points wrong.
All right, let's start reviewing. Any other topics in particular?
The wave stuff.
The wave stuff?
AC circuits, he hasn't listed.
Oh, no.
Reading before he...
I guess I could put this.
Sounds like an alien.
All right, I think that's pretty much everything that you would need help with. Okay. So let me maybe I just start by solving the Thevenin-Norton quiz. Is that fine?
Well, maybe something similar so we can get some points.
Maybe something similar?
Yeah, something similar to it, so we can solve the quiz ourselves rather than just looking at your answer.
Or doesn't it?
I mean, you can do that anyways. Have some self-control. I mean, I can just move the dots. I mean, come on, guys. It's fine.
Change the 9 volts to
I'll just change all the values. Nah, I got an idea. I know what I'll do. I will. The problems are all going to take these quizzes a little further. I just want you to know that. They're not going to be like the quizzes. Like it'll be like this, but there will be like an added current source so that you have to know, like, how does that affect everything? Like, it's not going to look like this. It's going to be similar to what you've seen, but it's not going to be exactly. All right, so this is quiz 8, and I'm doing Thevenin and Norton. Let's go with all right, how's that? All right, so the first thing I always ask is to find the voltage that we're actually interested in before you even do Thevenin and Norton. So let's just take the load as this resistor. So the first thing we're going to do is solve for Vx. It sticks out at me that I could do this really quickly as a mesh if you wanted to do it as a mesh. I can basically go boom, boom, call this I1, and I know I2 already. So if I wanted to do I1, I would basically go plus 2 volts minus I1 times 3K minus I1 plus, can I just write 0.5 milliamps? Is everybody cool with that? Alright, that's my first equation, and then obviously we have that I2 is just 0.5 milliamps. Any questions? Good? Alright, so now I'm going to go and, group like terms and whatnot in this equation here. So 2 volts. I've got a minus I1 3K, and then I've got a minus I1 6K, so that'll be a minus I1 times 9K. And then I've got a 0.5 milliamps and a 6K, which is going to give me a 3 volts. Alright, so I get negative 1 volts equals negative I1 times 9K. The negatives go away. I1 equals 1 volt over 9K, and what is that, like 0.111 milliamps or something? Yeah. Okay, so now I have I1 and I have I2. I need to find Vx. The current flowing through the 6K is I1 plus I2, right? So Vx is equal to I1 plus I2 times 6K, which is 0.11 plus 0.5, so basically 0.611. And this is no Thevenin and Norton yet, right? This is just finding Vx to start. So 0.611 times 10 to the minus 3 times 6,000 gives me 3.66 volts. Do we care if I do spice to prove it, or do you want me to just do as much as I can on paper today? No spice? Did someone say please do spice, or was it no spice? No spice, alright. Alright, so you're just going to trust me?
Yes.
Alright, so we're just going to assume that's right. Alright, so now we have Vx, which makes sense. It should be higher than 2 volts. If it was less than 2 volts, I'd be concerned. The reason is that I have 2 volt supply over here supplying power to that node, and I also have current being pushed into that node. Okay. So that makes sense. So now what we would do is we would Thevenize the circuit. The first thing that we want to do when we Thevenize is we want to get rid of the load, and we want to take the voltage across the load right, to determine V Thevenin. So let's do that first. Maybe I'll do what I did last time and split my paper into Thevenin. Alright, so for Thevenin, I'm going to remove the load and my new circuit's going to look like this. Right? Got ground, of course. 2 volts. 3K. This is 0.5 milliamps. And then this voltage right here, that difference is going to be my Thevenin voltage, right? Any questions so far? All right. So, what's this voltage right here?
2.
Okay, good. How much current's flowing through this 3K? 0.5 milliamps. So let's take that out of there. 2 volts. I got a 3K, and then I'm trying to find basically this voltage right here, and I know that I have a current of 0.5 milliamps flowing through there, right? Everybody sees how I just basically removed this little chunk and put it over here? Alright, so the drop across this is going to be 0.5 milliamps times 3K, right? So that's what, 1.5 volts? But note that it's going this way, right? Because the current's flowing this way. Alright, so that means I'm going from a higher voltage, dropping by 1.5 down to 2. So then what's V Thevenin? V Thevenin's 3.5. Any questions? Yeah.
I put it in spice and I got 2.3 volts for VX.
Right here?
Yeah,
So I did do something wrong.
maybe.
Let's see. It's probably a sign thing because I did a lot of skipping steps. 2 volts minus I1 times 3K minus I1 plus I2 times 6K equals 0. That's right. Then I went minus I1 times 3K minus I1 times 6K gave me a minus I1 times 9K minus 0.5 milliamps times 6K gives me 3 volts. 2 volts minus 3 volts gives me negative 1 volt. Yep, that's what I did wrong. This went over to the other side and it's plus. So that means that my current was negative 0.111 milliamps, I1. So 5, so this would instead be, this is why we need spice, guys. This would be 0.5 minus 0.111, which is, what is that, 0.389?
Yeah.
Good thing you did that. It seemed a little high to me too, so that's why I asked if you wanted me to do the spice.
I'll just put everything in spice.
That would be great. So that's 0.389 milliamps, and I multiply that by 6K, and I get 2.33. That's what you got?
Yeah.
So I get spice on the final one?
Nope. That would be just, that would be so disappointing. I think you'd be disappointed if you got spice on the final. Alright, so now V Thevenin should still be 3.5. I didn't do anything wrong over here. This is my VX. Okay, clean enough. Okay, so I've got V Thevenin. I always want to say V threshold because this is the same thing we use for threshold voltage. V Thevenin is 3.5. Now I guess the next thing I could do is I would find, do you guys prefer finding the resistance or the current? The resistance? Okay, so let's find R Thevenin. Alright, if I'm going to find R Thevenin, I want to open up current sources, right? And I want to short voltage sources. And then I want to measure the resistance between the two terminals. So my new circuit would be a short across the battery, a 3K, my load terminals, a 3K, and then another open. And I'm measuring the resistance between these 2 points. Basically, if I send a current in here, how much resistance does it have to go through to get to the other load terminal? It can't go this way at all because there's an open there, right? So all of it has to go through this 3K, which means my R Thevenin is 3K. All right. So, any questions about that? Yeah.
If there wasn't a current source there and it was just a wire and the voltage, or the Thevenin resistance had to go through 2 resistors, those would be in parallel, right?
Right, so then in that case it would be 3K in parallel with whatever this is. So if it were here, it'd be a 3K in parallel with a 3K, so your Thevenin would be 1.5K, your R Thevenin. So yeah, if I gave you like voltage source, resistor, voltage source, then that's how it would look. Those would both get shorted and your R Thevenin would be the 2 in parallel. Alright? That's right. So now if I wanted to find I short circuit, or I Norton, I guess you can call it, you can either do the other method, which is short across these 2 terminals and measure that current, or you can just say I Norton is V Thevenin over R Thevenin, which in this case it's 3.5 volts divided by 3K. So whatever 7 over 6 is, 1.166 milliamps. And that's I Norton. And then from here you would draw your equivalent circuits. Do I need to draw them? You want me to draw them? Alright, I don't want to take up a whole other sheet of paper. Can I do them on here? Do I have room anywhere?
I don't think so.
Here, I'll just go in Spice real quick. Then I don't have to draw it anywhere.
Could you call it back to me?
So this would be my V Thevenin. We just solved for it. It would be 3.5. And then it would have a resistor in series of R Thevenin, which was 3K, right? And so we would connect our load right out here. So just to clarify, in case it's not clear already. Whoops. This is my Thevenin equivalent. What's in that box is my Thevenin equivalent. And when I connect my load, all I'm doing is making sure that I got the correct Thevenin equivalent. This inside the box is my Thevenin equivalent. It's R Thevenin in series with V Thevenin. Everybody sees that? Yeah.
So on the final, would us doing just the Thevenin equivalent be enough, or do you also want us to put the load there?
Whatever I put as the instructions on that quiz is exactly what I put as the instructions on the exam. So let's see. First, determine V out. Except in the other problem, it's probably named something differently. Then find Thevenin and Norton equivalents when RL is removed, exactly what we just did. Confirm that your equivalent circuits are correct by plugging RL back into your equivalents and verifying blah, blah, blah. It's the same exact thing. So yeah, you got to plug it back in, make sure that they match. All that good stuff. Okay, so this is my Thevenin equivalent circuit. Does that make sense? You good with that? So my Norton equivalent is going to be my current source. And that is going to be in parallel with R Norton, which is the same as R Thevenin. And what did we just calculate? 1.166 milliamps. And again, this right here is my Norton equivalent. It's just that piece. And then when I connect my load, right, RL, Norton, all I'm doing is making sure that I got that correct. So this would be VX Norton. Alright, any questions? Yeah.
Are you using Evan and Norton often in electrical engineering projects?
No, not at all.
Okay.
However, there have been several problems I've had where Baker's like, why don't you just do a Thevenin equivalent? And I'm like, that never would have crossed my mind, but okay. So, I mean, I guess it could be useful if you really like it. I don't really like it. I think that it's easier. The thing is, you don't need it because you have simulation software. The whole point of this is if you don't have simulation software. I mean, you have to know why the simulation software does what it does. That's the whole point of the class. Because you can't design circuits by just shoving random stuff into LT Spice. You can design stuff. Yeah, you can design stuff like that. It's just that's just not a good way to design anything. All right. Any questions about this? Good. Any other questions about Thevenin and Norton, or should I go to another topic?
How do you find type of circuits?
Like the actual way?
Yeah, how do you actually find it?
Yeah, so if I wanted to find I short circuit, I would basically draw a wire right here. I guess I would do it in this circuit. It's in the one where there's actually sources, so don't look at that. I would draw a wire right here. And I would solve the circuit to determine what's the current flowing through that branch right there. So basically I have a current flowing right here, right? We could call it I1. And I have a current flowing right here, I2. The sum of those two currents comes into that node and then goes down, right? That sum, that's I short circuit. That's your Norton current. So you put a wire there and basically measure I1 plus I2. That will give you I short circuit, which is equal to I Norton. So if you wanted to do it, you could do it that way. You just put the wire there and solve for those currents and determine what that current is, right? Yeah, you could just use mesh, or in this case, well, the thing you'll have to note is that once I put a wire here, this is ground, right? That's 0. I just shorted that. So 2 volts minus 0 volts over 3K gives me that current. I already know this current, so I add those and I get the short circuit current. So real quick, 2 volts over 0, right? 2 volts over 0, or sorry, 2 minus 0 over 3K, that'd be 2/3, so like 0.66, right? And then over here I've got 0.5. If I added 0.66 to 0.5, I get 1.166. So that's how you do it. That's where it comes from. Anything else? What next? Mesh and superposition? Huh? A 5 loop? That's unnecessary. I'll do a 3 loop. We'll go look at the quiz. Did I give you a quiz with 3 or did I give you a quiz with 2?
No, I think you gave me both.
No, I only gave this.
But you get the, on the test, you get a 3 loop.
Okay, you want me to go solve something like that then? Let's go look. Yes. Alright, cool. Let's do something like this then.
He'll give us a 3 loop, but always give us a current with 3.
What's that?
I said, you'll give us a 3 loop, but you'll at least give us 1 current. Unless you're mean.
Unless I'm mean. You should know how to do both. I mean, it's the same process, right?
Yeah.
Yeah. Well, you know me well enough that you know how I operate. You should. Wow, I'm such a nerd. I literally just used an underscore. Are you kidding me? Who does that?
Apparently you do.
I guess I do. I wrote quiz 8 over there, and that wasn't quiz 8. It was derived from quiz 8. So I guess I'm going to write midterm problem 3, and I'm not going to solve midterm problem 3 now. I'm going to solve something similar.
Hey, there was people that aren't in class on.
Let's. Well, if they're not listening to the audio. Does anybody ever miss my class and just go look at the notes? That's so useless.
I had one
Has anybody done that?
once.
Just like, he didn't cover anything important. All right, cool.
Honestly, like, I just look at your notes for like the information. Okay, got it.
Yeah, that works.
Yeah. Basically is.
Contact prevention analysis.
I think that's a great idea. We should make a picture book of circles. Just for dumb.
I would love to do that.
For like 5-year-olds, so we can get it to snap. And then you can just pop each part of the circle like this is the resistor.
So what are the pop-ups going to be? Like all the different components or all the sources? Or?
Like like either voltage or
Here's how you do mesh theory.
Oh, look, here's a system of equations that pops up.
That would be horrible. One of the guys I work with gave his kid an oscilloscope as like a toy. Who does that? Like, come on. I'm not even kidding.
Was this something that his kid asked for, or was this just something he's like, oh, this is what a kid
What kid is asking for an oscilloscope?
How old was this
He's,
kid?
he's like 4.
Dude, there's some smart kids out there.
A smart kid's not asking for an oscilloscope.
I mean, like, if you're a kid, you're growing up with that, and then you get there, you're going to be growing up around that kind of stuff. Maybe you're interested.
I know it was by force.
By force.
All right, let's do it. All right, how's this? Look interesting? All right, let's do it. Let's go. All right. Let's go ahead and do this. What you'll find is that if there's a voltage source shared between 2 loops, it actually makes it significantly easier too, because then you don't have a resistor there, so there's no variables. All right. It's still going to be some algebra. I don't really plan on doing all the algebra. I'll just set it up. Is that fine? All right. So if I wanted to write an equation for I2, what would I write? Everybody sees that I2 is just 1 milliamp?
Yes.
Okay. If I wanted to write an equation for I3, I guess the first thing I would do is I'm going to drop here, I'm going to drop there, and then note that I3 and I1 are going in opposite directions at the 2K, so there's going to be a minus. So let's go minus I3 times 1K minus, now inside the parentheses I have I3 minus I1 times 2K, 0. Everybody good with that? Alright, and then for I1, I'm going to have one last equation. I'll go plus 2 volts minus, inside parentheses, I've got I1 minus I3 because they're going in opposite directions, times 2K, and then minus I1 times 4K, and that gives me 0. Alright, I've got 3 equations, I've got 3 unknowns. However, you'll note that these 2 equations are completely independent of I2, and that's because of the voltage source being shared. So you basically just have 2 equations, 2 unknowns here, and you just solve for I1 and I3, and then from there you can get the voltages. Does anybody want me to do it? No? Yeah? I would group the like terms in both equations. I would solve for one of them. And then, so say I go through this and I get I1 equals something times I3, right? Now I would take my something times I3 and plug it in for I1 in this equation, and then I have I3 in every case, and then I can solve for that one, right? And then from there, I know it shouldn't be challenging to find the voltages at that point because you have all the currents, all right? All right, so that's mesh. I guess I can do a superposition one too. See if I can solve this with superposition. Yeah. Yeah. All right. Let's say I wanted to solve this one for using superposition. I just did mesh up top. And I want to do this one using superposition now. All right, if I was going to solve it using superposition, you know, we have two cases. Basically, let's say I wanted to solve for VA. Or not VA. VA is always 2 volts. That's a bad example. Let's say VC. I want to solve for VC using superposition. All right. So first, I would draw the circuit without the current source, and I would solve it for VC. And then I would draw the circuit without the voltage source, and I would solve it for VC, right? And I add those two values, and I get my final value for VC. So basically, I could write VC1 plus VC2 gives me VC. And over here, I'll get rid of the current source first just because. So if I were to solve this, I'd have. This isn't open completely, so there's nothing going on over there. There's a resistor here, but it's not going to matter. All right. So basically, I could redraw this without the open, right? I'm just going to draw it a little neater because the open, no current flows, right? So that branch of the circuit is effectively useless. So if I'm going to redraw this, I would redraw it like this. And now it should look strikingly easy. Exactly. Everybody recognize that that's just a voltage divider? Stop. 2 volts. So yeah, it would be 2 volts times my R2, which is 4K, over R1 plus R2, where R1 is 2K in parallel with 1K, which is 0.66K, plus 4K. That would give me VC1, basically. All right. Any questions? All right, now I'm going to do VC2. So VC2 is when there's no voltage source. Yeah. I don't know. This could turn out ugly. This is me just coming up with problems on the spot. That's why I don't do this usually. But we'll see. So this is a short, right? That's my VC2. My ground is over here somewhere. So note, all of this is ground. All right. All right, this is kind of interesting. Let's see what's going to happen. I would never give you something that's going to end up this hard, because this actually looks really challenging. I might have to redraw it. The 1K and the 2K are in parallel, right? So I could get rid of... I want to like redraw it because this looks horrible. All right, so if I put the 1K and 2K in parallel, that's just going to give me 0.66K. So I basically have 0.66K, and that's connected to ground. And then there's a 4K. I might have ended up with another horrendous situation here, because that's also connected to ground, right? And then I've got a 1K that's connected to ground on one side. Yeah, this doesn't look good. It's basically like this. I don't think this is good, because what's going to happen is all this current is going to go like this, and then nothing's going to happen over here. It's like the same thing that happened the last time I tried to come up with a problem out of nowhere. All that matters is the gist of superposition, right? You get rid of the current source, solve for the voltage. You get rid of the voltage source, solve for the voltage, and then you add them. If you want me to do another one that's not hideous, I can. Spice? Yeah, let's do it. I don't think it's gonna scream at me. I just don't think it's gonna do anything interesting. I think it's gonna be 0, 0, 0, 0, 0 everywhere.
It'd be like nothing happens.
This is why I don't come up with problems on the spot. Somehow Baker's really good at it, but it's probably because they're in his head from 20 years of teaching, and they're not actually on the spot, right?
Yeah, they're not. It's just something he came up with like 7 semesters ago, and he's just like, oh yeah, I'm done.
Alright, let's see, what did I have? 1K, 2K, 4K, 1K, 1KJ, nope, and 1 milliamp. Of course. Alright, let's see what this VC gives me. 0, 0, 0, 0, 0, 0, yeah. Okay, so good. Alright, well, hey, if this was a problem and you got 0 there, then you would just add 0 to the original one. So that means that VC would be just whatever VC1 was. Alright. I can do a better one if you want. Does anybody want me to do another superposition, or would you rather me do something else? Do another one? Alright, I'll do another one. But then I have to think of one. Can I just do this one? Oh yeah, let me just go do a Baker one. That's a good idea.
Actually call Baker right now and ask him.
You're like, I need a question real quick.
It's a superposition question right now.
He just verbally explains to you his superposition questions and then work out.
Let's see if he's got any here. Yeah, but this is so easy. Alright, whatever, I'll do it. I can't, maybe the 3-loop superposition thing just isn't a good idea. Unless I think about it really hard and make it so that it doesn't turn out stupid. Okay. He says find Vx, which is over here. When you guys do these problems, a good idea, like a good general rule, is get everything in terms of K for the resistors, so that you don't go add 500K to 1K and screw everything up. So I wrote it as 0.5K. That's a good practice. Like this Baker Fall 17 midterm. What problem was it? 2. Nope. I don't know why I wrote that. All right, so again, I'm going to split the page into two. This time I should actually be able to solve it. All right, so first I'll get rid of the current source because that's really easy. All right, so first let's go, we got a 1.5. This is open. This is basically just a voltage divider. Does anyone not see that this is basically just a voltage divider? Everybody sees that? Alright, so that means that we've got Vx1 is equal to R, basically my input, R2, which is 0.5K, over R1, which is these two in series, right? 2.5K plus 0.5K. So it's 1.5 volts times basically 1/6. What is that? 0.25 volts? Really? 0.25 volts, that's what I said. Alright, that's the first part. Any questions? Alright, good. Second part is getting rid of the voltage source. So I short it. Current divider. Okay, so I basically have 1.5K at 1.5K. He made it that way. That's nice that he did that. That means that half of the current's going to flow this way and the other half's going to flow this way, right? So then the current that flows over here is just 0.5 milliamps. Alright, so if I have 0.5 milliamps flowing across 0.5K, that's going to give me 0.25 volts there, so Vx2 is also 0.25 volts, which means Vx should be good. Did you put it in spice? No. I think it should be fine. I trust me on this one. Alright, cool. Any questions about superposition? Where's the list? Alright, what else? What next?
Dependent sources.
Dependent sources? Okay. Let's go look at that homework. I gave 4 different types. Or let's just see if Baker did anything on the midterm.
Is this final on there?
No, he doesn't post his finals. He probably keeps the same final for the last however many times he's taught the class. Take some time to write these exams, because you actually do have to figure out if the problems are going to work out.
You can't just come up with one.
I mean,
That is a huge
how much a share?
It's a gallon. Yeah, I know. I used Spice to help me. Alright, should I solve this one? Is this fine? Or did you want me to like go over dependent sources again, like all the way? Like the 4 types.
Just like a quick rundown of the 4 times, yeah.
Let me do a quick rundown of that and then we'll do this problem. Alright, so I think many of you will find that this is the most useful class you'll ever take. Yeah. I mean, if you continue on in EE and do anything with circuits, you're going to remember this class and be like, yeah, that class taught me all the fundamentals. That's right. Oh, Jesus. You guys are insane. All right, so there's these four types. There's current controlled voltage source, current controlled current source, voltage controlled voltage source, and voltage controlled current source. Alright, those are your four types. Let's go look at them in SPICE real quick. I think it's like E, F, G, H. E is voltage controlled voltage. F is current controlled current. G is voltage controlled current, and H is probably current controlled voltage. Yeah. So those are your four types right there. Basically, in order to use the current controlled sources, you have to go and put a voltage source into the circuit somewhere, a 0 volt source, to get the current through it, and then you're going to multiply that by this gain value, whatever it is. The voltage ones are a lot easier because you can just pass the voltage difference in using these inputs. That's not going to matter on the exam because I think that I stayed away from the current controlled ones because it's just too much to think about. I don't think it's too much to think about. Baker didn't think so either. He gave you a current controlled one. So we'll solve this, but I think mine's voltage controlled. But basically, if it's current controlled voltage, that means it's taking in a current, multiplying it by some gain, and outputting a voltage. So the type of source is the second half of the name, and the type of input is the first half of the name. All right, let's go solve Baker's example. That was a waste of a piece of paper. I should have done it smaller. It's okay. These all get recycled. No. Yeah, they're kept forever on my webpage once I scan them. Alright, so you see, right, VM is the 0 volt source. It's being used to measure the current. He references VM and then multiplies it by 3. So whatever the current through VM is, don't be the person who goes, VM is just 0, which means it's 0. It's not a voltage source. It's meant to measure current. Someone will do it, don't you worry. Okay, here we go. 1.5, 500. I'm not even going to draw the current source or the voltage source. One thing you'll find if you haven't already is that in order to do well in this field, you really have to go above and beyond what's expected of you. Like if you want to do well on this exam, like truly you want to get an A, you're going to have to study more than just the stuff I'm going over. And that's not because I'm going to give you problems that you couldn't do if you knew this stuff very well. The problem is you don't know this stuff very well unless you solve a bunch of problems. If you just solve the problems I'm going over right now and slight variations of them, that's good. You're probably going to get a good grade, but you're not going to get a great grade. So just that's the general. I mean, and in my class and Baker's classes, it's a lot easier than professors who don't even tell you what they expect. I'm just gonna to make this easier, I'm going to call this I, and I'm going to put 3 times I. Is everybody fine with that? Just so you, you're not even looking at the paper. I'm calling that I, and I'm calling this 3 times I. But the important part is being able to look at this and knowing that that's what's happening here, is that what I'm taking is the current through this voltage source and multiplying it by 3. All right? So I think I got everything written down now. And then ground, of course. All right. Let's go with... can anybody just look at this and tell me what I is? It's 1.5 volts over... Oh, you meant this one?
Yeah, you did with that. Actually, he said not to do.
What did I say not to do?
He said don't look at it and just be like, it's 0. He looked at it and was like, it's 3.
Well, yeah, it is 3. He was a step ahead. This is 3. This is 1 milliamp because this is 1.5 volts over 1.5 K. Everybody see that? All right. And then that gets multiplied by 3, so my current over here is 3 milliamps flowing. Was that counterclockwise? All right, so if I wanted to find V out, my drop is 3 milliamps times 1K, or 3 volts. So what's V out? Should I do another one? That felt too quick. Let's see if we can find another one. We'll go to like, I don't know, let's go to one of his recent ones. It's the same problem. How lame. He's so lazy. He always says, I'm so lazy, guys, I just modify one thing. Now I'm seeing it. Well,
you can look at 4 years of work side by side though.
When I took his class, he never posted the quizzes, he never posted the midterms, we had nothing. He recently did all this. He recently started posting exams. But when I was in his class, there was no practice exams. So it was a lot harder. Where was I looking for? The lecture notes, the midterm? It's going to be the same, isn't it?
It's a little different.
Yeah, but you're not learning anything. I'm doing the same stuff. Oh, no, I guess this is slightly different. We'll solve this one. So this will be Baker F16 midterm problem. What is this, 5 again? Alright, so we've got a 3 volt source, 1K. The current I'm interested in is this current. And then I've got a 2K. And then this is 1 milliamp, this is 2K, this is V out, and then this is, I guess he called this VH, and he's multiplying this by 1K. Interesting. Alright. V huge? Is that why? It's not going to be huge. You're taking milliamps of current multiplied by 1,000, it just cancels.
Well, I was saying he called it VH because the source its name is H1.
Oh, that's why.
They called it VH.
That makes sense. Alright, so this is 3 volts. What's I? 1 milliamp. Look how nice he is. It's because he's lazy. And he grades the exam, so he wants it to be easy for him. It has nothing to do with the students. I think it has everything to do with the fact that he wants to be able to look at it that easily. not waste any brain power. All right, so 1 milliamp times 1K. What's VH? All right. And so now in order to find V out, we have to determine the drop across this 2K, right? So I've got current flowing this way, 1 milliamp, right? So I have a drop of what across that 2K? 2 volts. I'm going from a lower to a higher, so what's V out? It's 3 volts because it's going from a lower voltage to a higher voltage by 2 volts, okay? Any problems here? Any questions? We got about 15 more minutes. Let's see if we can cover one more of these, and then the rest we'll cover next time. Dependent sources, check. All right, what else? What next? Charge sharing? Cool. Should I solve quiz 11, or should I do something else? Yeah. So let's go over it real quick, and then I'll solve quiz 11, and then we'll get out of here. How does this marker look? I haven't used it all semester because I thought it would look like crap. Nah, it's not good. It's not good at all. I haven't used black either, really. I guess I have.
You should rewrite yellow.
Black and yellow? Yeah. I wonder if subliminally that's why I grabbed the black marker next. You think so?
Stuff is on, you're like, yeah.
Let's consult a psychologist. All right, so charge sharing is when basically charge is conserved in this particular process where if I have a capacitor sitting here charged to some voltage, we'll call it VC, and this is a capacitance with a value C, right? That capacitor stores Q charge, which is C times VC, right? CV equals Q, that's that equation right there. The voltage across the capacitor times the capacitance gives me the total charge stored by the capacitor. Well, let's say I've got another capacitor, let's call this C1 and VC1. I have another capacitor somewhere else with a different voltage across it, VC2. I can say that the charge Q2 stored on this capacitor is that capacitance times that voltage across it, right? And so if I were to connect these in a circuit, and this switch is open, initially nothing's happening in the circuit, right? Because these two capacitors are basically just floating there charged. And what causes a capacitor to discharge is some current flowing, some difference in potential, which is voltage, causes the charges to redistribute. And so when I switch this switch shut, what happens is I end up with these two capacitors in parallel. So my new capacitance, when the switch closes, is C1 plus C2, right? They're parallel capacitors, okay? And now, once this node is just one big node, and initially I had a node where this was VC1 and this was VC2, but when I shut the switch, I end up with a new voltage, which is just one value, right? Because they're in parallel. It can't be one voltage here and one voltage here if this is just one long wire, right? And so what basically happens is V new is equal to, well, what was this equation was C times V equals Q. So if I redistribute, I get V is equal to Q over C. You see that? So my V new is going to be equal to some value Q over my new value of C. Well, that value of Q is the initial sum of these two values because charge is conserved. No charge is lost. So the amount of charge that was initially stored on this capacitor plus the amount of charge that was initially stored on this capacitor, I'll call that Q total. That was equal to Q1 plus Q2. And so in this equation I can just write Q total right here. And that's going to give me, the question I ask typically is what's the final voltage, right? Because the charge is conserved and you know the capacitors add. And so That's what happens. That's charge sharing. Charge sharing is important because it's used to move voltages around inside of a circuit when a switch closes. It's like a trigger. Like we press this button, the switch closes, something happens, and then the circuit responds based on this voltage either getting pulled down or getting pulled up, whatever it may be. I talked about how we use it in DRAM, and that was what quiz 11 was. So in this bottom corner, I'll solve one of them so I don't waste paper. Question?
About like when the gate closes, do C1 and C2 typically have the same charge, or
No. So basically in DRAM, the way I did the quiz was exactly what happens in DRAM. So let's go look at it. Quizzes. That was quiz 11. So in DRAM, you've got basically a bit line. It's a line, like just a wire, that's connected to a bunch of rows in the memory array. And then you've got a memory bit, which has an actual capacitor inside. And those two capacitances are different, typically by a factor of 5 or 10. And so what they do is they store, I think I literally wrote it all here. Maybe I didn't talk about it in any great depth because I didn't want to overwhelm anybody. But the bit line is charged initially to 500 millivolts, which is half of VDD. They usually use a power supply voltage of 1 volt, so half of that is 500 millivolts, okay? And so in this quiz, what I did was I charged one memory bit to 1, which is a value of 1 in binary, and 1 to 0, which is a value of 0 in binary. And I showed that when the switch closes, basically this node will get pulled up a little bit from 500 millivolts, right? Well, if you did this right, what you should have seen is that this goes up to like 583 millivolts. So if that little change from half of VDD to a slightly higher value, now the circuit can determine that there was a 1 stored in that cell. And over here, if we use 0, when this closes, this bit line gets pulled down by 83 millivolts to a smaller value, and now the circuit can determine that there was a 0 in that cell. So the whole point of this is, well, I mean, not the whole point, but it's used in memory. And all you really have to know is that when you initially have a voltage here, you initially have a voltage here, and when you close this, that voltage gets changed to some value in between those two voltages. So when you do this, if you do it right, so say this was 1 and this was 3, and this was 3, your new voltage should be between 1 and 3. If it's not, then you did something wrong. All right. So I have 5 minutes. Let me do an example from this quiz. I don't really need to do it from this quiz. I can just pick some random values. Did I answer your question or no? Yeah. All right. So let's say this is 2 microfarads and it's initially charged to 3 volts. And we'll say this is 1 microfarad and it's initially charged to 1 volt. My new voltage should be between 1 and 3, okay? If it's not, then something's wrong. Alright, so Q1, we'll go over here. Q1 is equal to C times V, 3 volts times 2 microfarads. What's the unit for charge? Coulombs, so it's 6 microcoulombs. Q2 is 1 volt times 1 microfarad, so that's going to be 1 microcoulomb. So Q total, what is it? The starting... Alright, so I've got my Q total. What's my final capacitance after the switch closes? Alright, so I know CV equals Q, so C final times V final equals Q total. So I can rearrange this again. I get V final is going to be Q total over C final, or 7 microcoulombs over 3 microfarads. What's 7 divided by 3? Therefore, V final is 2.33 volts. Good? Any other questions last minute before we get out of here? And we'll do this again next time with the other topics.
What was the term clockwise and counterclockwise for officers that
That's a great question. I can't answer that.
Sundial wire and sundial wire.